let's take what we know about graphing polynomials and apply them to expressions with rational exponents. With this polynomial function, we can find out a lot of information about the graph without the use of a calculator. Things like x-intercepts, y-intercepts, end behavior, and even domain and sometimes range can be found, all with our algebraic work. Let's start with x-intercepts. X-intercepts can be found by calculating our x value when our y coordinate is 0. So in this function, f of x is x to the third minus 4x, I can replace the y or the output with 0 and solve for the x. And when I look at the structure of this problem, I see that factoring could be a strategy I use to solve. Noticing that both terms in front and after the minus sign share an x in common, I can factor that out at the greatest common factor, leaving behind x squared minus 4. I could even factor this further, recognizing the difference of squares, x squared minus 4, which will factor into x plus 2 and x minus 2. Solving by factoring is nice because if you have three things multiplied together to get a product of 0, then that means one of those items has to be 0. So we can set up individual equations for each one of these factors. What if x was equal to 0? What if x plus 2 was equal to 0? Or what if x minus 2 was equal to 0? And that will lead us to our three x-intercepts of 0. Solving the second equation, I would get negative 2. And solving the third, I would get 2. This function for f of x has three x-intercepts. I can solve for my y-intercepts by saying let's discover our y-coordinate when our x-coordinate is 0. I could use the function notation and simply evaluate f of 0, or I can just think about plugging in y for f of x and 0 anytime I see an x. Performing those calculations, 0 to the third minus 0 gets me a y-intercept of 0, and my sketch is starting to come together. I can quickly plot an x and a y axis with x-intercepts of 2, 0, and negative 2, and my y-intercept of 0. When I learned about polynomial functions, I learned that I can use two things, the degree and the leading coefficient, to determine the end behavior of my polynomial graph. When I talk about the degree, it corresponds to the highest exponent of the function when written in standard form. So since this says x to the third, the degree of this polynomial would be 3. The reason why that's important to us is that this highest exponent has the largest impact on the magnitude of our outputs. If that degree is an odd number, like we see here, what that tells us is that the end behavior of our graph is opposite of one another. So we could either have this situation, or we could have this situation here. We don't know which one. That's where combining it with the leading coefficient will be helpful. The leading coefficient is the coefficient in front of that term with the highest exponent. In this case, it's 1. And I'm really not worried about the fact that it's 1. I'm using the fact that it is a positive number. That helps me to know that I'm looking at a graph with this end behavior. As x approaches infinity, I should see my graph having positive end behavior. So let's bring that up to our picture. I'm going to have end behavior like this, and I can fill in the blanks. As x approaches negative infinity, that's just a fancy way of saying we're considering what's happening as I move to the left on my graph, my heights are going downwards and decreasing without bounds. So I would say f of x approaches negative infinity. And as x approaches infinity, meaning as I move to the right indefinitely, then my heights will also approach infinity. I can go ahead and think about how I would move from my original end behavior down here bottom left up here to the top right while using these x-intercepts. We have a topic called multiplicity that we encountered from Algebra 2 that talked about how our graph will behave at each one of these x-intercepts. And I can look at the factored version of this polynomial function. Notice I have x to the first. That means at my x-intercept of 0, the graph will behave like a line. It will cross through the x-axis. I will see the same behavior with the x-intercept at negative 2 and at positive 2, because in each case the multiplicity is 1. So let's see if we can sketch this graph. Starting down here, I will increase, crossing through the x-axis at my first x-intercept, and at some point I need to change to decreasing and cross through the x-axis at 0. And again, change to increasing and cross the x-axis at 2. This provides the general shape of this cubic function. You may be thinking about these max and min values. With calculus, we'll be able to determine those exact values. For us right now, we would require the use of technology to determine the exact values for these max and mins. Using our illustration, though, I can see that the domain is all real numbers, and that visual is helpful, but I can also be thinking about what I'm asking of my inputs. I'm taking an input value and I'm cubing it. I can cube positives and negatives and 0 with no problem. I can use that same sort of thing to examine what would happen if I took -4 times an input. All numbers would be possible. The range is able to be determined in this instance because of that end behavior. I can see that this graph will approach negative infinity as well as positive infinity, and because the domain is continuous, I would see it include every single height in between. So now that we've seen this review of polynomial functions, let's compare this to something new. Look at the structure of this problem here. In many ways, it feels very similar, but it definitely is different. This is not a polynomial function, so I won't be able to use the same exact vocabulary or reasoning, but I might be able to draw some parallels. Let's calculate the x-intercepts in the same way as I did before. Let's find our x value when our y value is 0. And once again, I plug in my y for the output, and I'm left to look at how to solve this equation. Factoring is also a strategy here. In front and after the minus sign, I see that both of these expressions have x, and I can factor out the one with the lowest exponent, leaving behind the leftovers, 2 items separated by subtraction. If I take x to the 4/3 and factor out an x to the 1/3, I get x to the 3/3. If you'd like to see that, you can think of it as division. X to the 4/3, divide out that GCF. I can think of canceling. X to the 1/3 canceled from x to the 4/3 would leave x to the 3/3, or I could apply my exponent property saying if you're dividing things with the same base, subtract the exponents. I get x to the 1st. Continuing on, my term of -2x to the 1/3, if I divide out the x to the 1/3, I would be left with just 2. And this is the factored version of this equation. Setting each factor equal to 0, I can solve for my x-intercepts. So x to the 1/3 equals 0, and x minus 2 equals 0. This equation on the right is a lot easier to deal with. Just add 2 and I get x equals 2 as an x-intercept. And this one on the left, you might be able to mental math it, but I want to make sure we have the algebra skills to back it up. When I see x to the 1/3, I recognize that that's really the same thing as just saying the cube root of x. Remember, when you see a fraction exponent, the numerator would be considered the exponent, the denominator would be the root. So algebraically solving, I could cube both sides and come up with another x-intercept of 0. Y-intercepts can be found by plugging in 0 for x to determine our y-coordinate. Or in this case, you could evaluate f of 0. I like to put y equals, and then 0 to the 4/3 minus 2 times 0 to the 1/3. And in this case, 0 minus 0 is just 0. Again, the graph is starting to come together. I can see an x-intercept of 0, an x-intercept of 2, and a y-intercept of 0. Before I consider end behavior, I need to make sure that both of these expressions would be valid. Does the domain of this function include numbers towards negative infinity and numbers towards infinity? And in order to think about that, it might be helpful to rewrite our expression on the right-hand side using roots instead of those exponents. Remember, when we see something like x to the 4/3 power, I can think of that denominator as a root and the numerator as an exponent. So I could rewrite x to the 4/3 as representing the cube root of x to the 4th power. And I can choose if I want to put the 4th in the radical or outside of the radical. Minus 2 times the cube root of x. So what I want us to think about when we consider the domain is the root. A cube root, what would be the domain of a cube root function? Well, it would be all real numbers. I can cube root positives, I can cube root negatives, I can cube root 0. So here, that is what's playing into our domain conversation. If the root, so when represented as a fraction exponent, if the denominator of that rational exponent was an even number, that would indicate an even root, like a square root, and we might need to consider then domain restrictions since we cannot take the even root of a negative number in the real number system. You may be able to conceptualize what's going to happen with the end behavior. Imagine plugging in a really large negative number. Let's think about that. What if I imagined plugging in a negative infinity? I know that seems strange, but just go with me. If I plug in a really large negative number and I take it to the fourth power, that would be a really large positive number, which I would cube root and get a positive number. Notice how both of these terms have a cube root of a negative infinity? So really, it's this 4, much like the degree of a polynomial function, that's going to have the biggest impact on the magnitude of this number. So yes, I'm cube rooting a negative, which will get me a negative, but then I'm raising it to the fourth power. That's going to get me a very large positive number. So I'm going to tentatively say I think that as I plug in really large negative numbers, I will get a positive output. Similarly, if I think about what would happen if I plugged in a really large positive number, well, again, both of these include me taking the cube root of a very large positive number, but this first term also says we're going to take it to the fourth power. That's going to be significant and create a very large positive number. I'm thinking both of these sides will approach infinity. Let's take a look at what our calculator has to say about this graph. Here's the graph of our function. I can see the x-intercepts of 0 and 2. I can see again that y-intercept would also be 0. My end behavior prediction was correct. As I go to the left, my graph is approaching infinity. As I go to the right, my graph is approaching infinity. And I can see here that there's a minimum value of my graph. That would be helpful in determining the range of this function. With calculus, I could do this work by hand, but without those skills, I'm going to rely on technology to help me determine any mins and maxes. So with this statement here, I can say that the minimum value is approximately negative 1.191. Bringing that back to the range, that minimum value of negative 1.191 up to infinity. And I'm going to say it includes that value. I could sketch that minimum point, which occurred at approximately x is 0.5, and then my negative 1.191, and just kind of mimic the shape that I witnessed on my graphing calculator. So even though this is not a polynomial function, I can use those skills that I developed last year in Algebra 2, as well as my new skills of factoring with rational exponents to still create a good graph, using technology to support my thinking along the way.